So, okay, let us thank Fernando for his talk, and let us try to move on. Fernando, thank you very much for your presentation.
Thank you.
And we can come back at the end of the presentations. So let me make, again, repeat this announcement. Most of you can do a question, make a question directly by pushing this button in the upper right side of your screen, and then either you have already granted the permission to do the to make a question, or else we can grant it for you. So push it anytime you wish. But let's try to have the questions at the end of the presentation. In principle, Jan's talk is now our following speaker. So let us go directly to Jan's presentation on motility-induced interparticle correlations and dynamics. Jan, thank you very much for being with us and for bearing with us all these technical difficulties. So please go ahead with your presentation.
Actually, I have to apologize for the chaos in the beginning.
No. It was our, we made any effort to foresee any difficulty, but I mean, you never know where it fails. But anyway, we are very happy to see you.
So I had the assistance of an expert who is still standing next to me.
Good.
Thank
you very much. Okay.
You?
Yeah, you can go ahead and share your screen and start your talk. I also need a technician and somebody 40 years old, younger than I, to handle all these type of incidents.
So now I have problems sharing the screen, but the expert next to me is helping me.
Okay, that's okay. Take it easy.
So the point is,
even the expert has some problems now.
Yeah.
I'm sorry about this. This is really unbelievable.
No, that's okay.
Excuse me, it's because it asks on the permission, so we have to make some permission for this one, but it does not really allow us at the moment. So,
Fernando, what did you do to share your screen? Was it easy? What?
Yes, only push the button with the screen. The though is because it's a red line crossing, but it's no problem.
Okay, thank you.
So excuse me, it asks us that we have to keep on the web browser and reopen. So sorry for the inconvenience. We have to reconnection at the moment.
Okay.
Yeah.
So we have to reconnect?
Yeah.
Okay, in the meanwhile, if there are more questions for Fernando, we can use this time well. I actually had a question, Fernando, in trying to explain these non-equilibrium structures for the magnetic particles. You are using, let's say, seems like an equilibrium formalism. Are you using some form of local equilibrium assumption? I mean, we can talk about that later and in private. But anyway, if you have any comment on that.
I think that I assume that local equilibrium, and also local stationary condition in some systems. For example, in magnetorheological fluid, I use that.
Okay, thank you.
So we know. So can you see my screen now? Hello, can you see my
Yeah,
screen?
now we can see your
Yes.
screen, Jan.
You can also hear me?
We can also hear you.
Unbelievable. I'm sorry about this.
Thank you, Jan. Go ahead.
Yeah. What's this? No. So, the title of my talk is Motility-Induced Particle Correlations, and this is work that I've been doing together with Wim Briels, who is a good friend of mine from the University of Twente, and Hugo Park, who is a PhD in Jülich, and he just helped me. He's an expert with MEC. So let me first explain what the motile particles are, and then explain what interparticle correlations are, and then start with the real stuff. So motile particles are particles that are self-propelled, so they act with a force onto the fluid in which they are embedded. And there are many different types of such motile particles. So the classical examples are, for example, so bacteria, who push themselves through the fluid by the motion of these flagella. So so bacterium acts with a force onto the fluid and pulls itself through the fluid. There are also many synthetic particles, the most famous of which is maybe such genus particles, which are embedded in a solution of peroxide. And one side of these particles is coated with gold, and gold is a catalyzer for the decomposition of peroxide so you start with 2 molecules, and upon decomposition you end up with 3 molecules. So the number density of molecules at the gold side of this particle then increases, and that leads to an osmotic pressure difference that pushes this particle through the fluid. So there are many different types of these kinds of motile particles. Now, in the stationary state, the total hydrodynamic force of that particle is 0. So the force that it exerts onto the fluid by itself is then balanced by the friction force, and the friction force for a spherical particle is the friction coefficient, where this A is the radius of the sphere, multiplied by its velocity. So the velocity that it will attain is the proportional, of course, to the propulsion velocity divided by the Stokes friction coefficient. But on top, of course, of this translational motion, you also have Brownian motion, both translational and rotational. And what rotational Brownian motion is doing, it changes the orientation of the core and thereby the swimming velocity. So let me next, maybe it's not really necessary for this public, but to be on the safe side, let me just explain what interparticle correlations are. And these are quantified by the so-called pair correlation function, which is proportional to the probability density function, the PDF, to find a particle at position I1, and at the same time at another particle at position I2. So if these two particles do not interact with each other, of course this P2 will factorize into 2 P1s. If, however, the particles do interact, either directly through a pair interaction potential or via other particles, then of course this factorization does not hold anymore, and you have to correct this by adding this factor that is called the pair correlation function. So this pair correlation function quantifies the degree of correlation between these particles. Now, if you go to very dilute systems without swimming, so for passive systems, of course this G of R is nothing else but the Boltzmann exponent of the pair interaction potential. Now, for motile particles, this is not at all true anymore. So the G of R is not anymore equal to even at low concentration, not anymore equal to this Boltzmann exponential. It depends now also on the use, but even if you cannot define a potential such that even at low concentrations, the G of R is given by this expression. So even at low concentration, the pair correlation function for motile particles is not known. Now the swimming direction is characterized by the orientation of the particle. So this is a unit vector that points along the swimming direction of that particle. And of course, this direction of swimming will change due to rotational Brownian motion. Now I'm going to talk about active Brownian particles, or ABPs, which are defined as particles which have no hydrodynamic interactions. So I will neglect hydrodynamic interactions between these particles and ask then for how the pair correlation function looks like. Now the point of departure is of course the Smoluchowski equation. And the Smoluchowski equation is an equation of motion for the PDF of an assembly of n particles. And of course that function depends on the positions, but for the swimmers also on the orientations, which define the swimming direction as if it were alone in the unbounded fluid. So the rate of change of this n particle PDF is a sum of 3 parts. The first part describes a translational diffusion, where this is fixed diffusion term, or the Brownian diffusion term. And of course there is a probability flux that is due to interactions between the particles. So this psi is the total interaction energy between the particles. Then there is a contribution due to rotational diffusion, where this dr is the free rotational diffusion coefficient at infinite dilution, and this d naught here would be the translational diffusion coefficient also at infinite dilution, and these r's here are the rotation operators. They act on the orientation dependence of this Pn. And then for the motile particles, you also have a probability flux due to the translational swimming motion, which has this form. So this V naught was this velocity that I showed before, and this U is the orientation in which they swim. So V naught multiplied by this unit vector U would be the velocity of swimming of that particle without interactions with other particles, including its swimming as a direction. Now you can integrate the Smoluchowski equation over all degrees of freedom except that for one single particle, and then you get an equation of motion for the density, the number density of motile particles at position r with a particular orientation u. So if you integrate the Smoluchowski equation, you find an equation of motion for this density. And there are 2 parts. So one part is due to free motion without interaction with other particles. And then there is this complicated term which contains this G of R, which describes all the interactions. Now, if you know this G of R, then in principle you could calculate the phase behavior and the dynamics of the entire system. So this G of R is an extremely important function. If you would be able to have a good approximation for this G of R, you would be able to predict the behavior of the entire system, phase transitions, as well as dynamics. So this G of R is very important, and that's why for passive systems, there are hundreds and hundreds of papers trying to calculate this G of R, also at high concentrations. For active systems, for motile particles, there is absolutely nothing yet. So I'm going to calculate this G of R, but I will do that, as I said, for low concentrations where binary interactions between these particles are dominant. That in itself is already a difficult problem. Now, the point is that this G of R in this integral is multiplied by the gradient of the pair potential. And if you are interested in instabilities leading to phase separation, like spinal decomposition, for example, you have long density wavelengths that grow relatively slow as compared to the relaxation of sort of wavelengths that are much smaller than that long wavelength. So you can take for this GOR, because it relaxes almost instantaneously to the local density, you can take the stationary solution of the equation of motion for this GOR, which is some kind of a statistical analogon of local equilibrium. You can look at the stationary value of this GOR and still predict this decomposition kinetics when you have any kind of instability. So you can also integrate the Smoluchowski equation with respect to all degrees of freedom except for two particles. And then you get and you neglect the contributions from higher order, so for higher concentrations. So we're going to look at concentrations which are sufficiently small that binary interactions are dominant. And we are going to look, as I said, at the stationary solution, which is enough to calculate the dynamics of all these possible instabilities, which of course only occur at high concentration, but I focus now, of course, at low concentration. And I write this equation of motion with the GOR in a dimensionless form. So for example, the distance between two particles is now non-dimensionalized with the diameter of the particles, so that at contact, this dimensionless r is equal to 1. So if you do that, you get this dimensionless equation of motion, where this is the gradient with respect to this dimensionless r. And the important point is that this term describes the effect of motility. So this big U is the difference in orientation of the two particles, which is proportional to the relative velocity. So you can imagine if these two orientations are equal, the particles move aside with the same velocity, and that will have no effect on the GOR. But of course only when you neglect hydrodynamic interactions, which I've done. And then you have this prefactor, which is called the swimming Piclet number, which is equal of, so it's a dimensionless number, which is equal to the size of the particle multiplied by this swimming velocity, divided by the free translational diffusion coefficient D0. And so this number describes the relative importance of displacements due to motility divided by the displacement due to Brownian motion. So if this number is large, the dynamics will be dominated by the motility. If this number is small, the dynamics will be dominated by Brownian diffusion. So this is the important term. And of course you have two second order differential equations, so you need two boundary conditions. And one of them is the no-flux boundary conditions, which says that these cores cannot interpenetrate. So I'm going to stick to hard spheres, to hard sphere interactions. And this means that this no-flux boundary condition actually says that the cores cannot interpenetrate. So I'm looking at hard spheres. And then, of course, if the particles are not correlated anymore at large distances, as we have seen, this G of R should be equal to 1. So this is the set of equations that you need to solve to obtain the G of R in the stationary state at low concentrations for these active swimming particles. So you can ask first, what kind of symmetry do you expect? In other words, which are the important variables on which the G of R could depend? Now here we have these two particles with an orientation U1 and particle 2 with an orientation U2. And then this difference is the relative swimming velocity. Now you expect a cylindrical symmetry about around this line. So what you would do is to introduce the z-coordinate of the relative distance between the centers of the spheres, which is, of course, the magnitude of r multiplied by the cosine between this relative velocity and the center-to-center distance. So that I will call the z-coordinate, and you have the cylindrical distance, which is r times the sinus of that angle. So you have to imagine that there is a cylindrical symmetry about this u, the relative swimming velocities. So we have three important variables: the distance, the magnitude of the distance between the centers, the magnitude of the relative velocity or the relative orientation of the two particles, and then the angle between these two vectors. Or in other words, it depends on z, rho, and the magnitude of u. Now, the first thing to do is to look at small Piclet numbers. That is to say that Brownian dynamics is dominant over the swimming velocity. If you put this expansion into the original equation that we had, and you expand to linear within lambda, you get an equation for this G1, which looks like this, and you can solve that, and this is the solution. And you see there is a cosine theta here, which means that there is a symmetry where on one side there is an enhancement where the cosine is negative, and there is a depletion of probability, so the G of R is smaller than 1, for the cosine is positive. Now you can understand this intuitively as follows. So I will call this, where the particles approach each other, I will call that the front sector. And you can imagine if a particle comes in from below and collides with this excluded volume, so it collides with the other sphere, then of course you have an accumulation of spheres on this side, meaning that the G of R will be a little bit larger for the small lambda, a little bit larger than unity. And if the particle passed the central particle here, so it moves like this, then of course it takes a while by Brownian diffusion to fill up the depletion zone here, so this probability shadow. So the particle moves along, and it takes a little bit of time to move inwards to make the G of R equal to 1. So that means that there is here a depletion of probability, and I will call this side where the cosine is positive, so where the particles move apart, away from each other, I will call that the wake sector. So the front sector, they move towards each other, this cosine is negative. The wake sector, they move apart from each other, and so I will call that so the wake sector where the cosine is positive. Now what about very large lambda? What would you expect intuitively if the particles move with a very large velocity towards each other? You expect a very enhancement of the G of R, an accumulation of particles at the front side. So the contact value of the G of R will be very large. That is what you expect intuitively. And the range where this happens will probably be small. Actually, I will show that the contact value is proportional to the Piclet number, and the width of this so-called boundary layer is goes like 1 over lambda, and lambda is a large number, so this is a very narrow region, and then it slides along and then moves into the wake sector. Now that you have such a small boundary layer with a small spatial extent of 1 over lambda, you can also see this so mathematically from the Smoluchowski equation for the G of R. So now you multiply through with 1 over lambda. So 1 over lambda is now the small number. If you simply say I'm going to skip all the terms proportional to 1 over lambda, being the small parameter, you're left with a first order differential equation. But you have two boundary conditions, and you cannot adjust the single integration the integration constant from a first order differential equation to match two boundary conditions. And that means that this second order derivative, which is multiplied by 1 over lambda, must be of the same order of the other terms. So this means that these derivatives should be very, very large, of the order of 1 over lambda, of the order of lambda, in order to be able to to fit two of these boundary conditions. Now, the G of R can only be steep if that happens in a small region, and that small region is called the boundary layer in mathematics. And this is a typical example of a so-called singular perturbation problem. So what you do in such a theory is that you spatially extend the distance from the surface. So this would be R1, and you spatially extend this thing such that the second order derivative becomes of order 1. So if you introduce this boundary layer variable, which is lambda multiplied by the distance from the point of contact, so R minus 1, then you stretch, so to speak, this region so that these derivatives are well behaved, so to speak. So this is the gradient operator with respect to this so-called boundary layer variable. And you see that the rotational part is multiplied by 1 over lambda squared in that case. So rotational diffusion will not be important. And you end up with this very simple equation, in terms of the boundary layer variable. The interpretation is that this term is not important because time that these particles actually are close together for these large relative velocities is so small that rotational diffusion has no time to take place. So you can solve this equation, and what you obtain is here an R minus 1 multiplied by lambda. So you see that if R minus 1 is of the order of 1 over lambda, then the G of R almost relaxes to unity. So you have, this is a contour plot of this solution. And you see again this, the solution of the Smolkowski equation, and you see that you have this narrow region, so this boundary layer, and the contact value is very large. So remember that in the front sector the cosine is negative, so the contact value varies linearly with lambda. So you have a very large contact value in a very narrow region where the G of R is not unity. And as I said, rotational diffusion can be neglected, so translational diffusion is dominant in the front sector. Now, what about the wake sector? Of course, in the wake sector, the cosine is negative, and then for large R, this thing will explode. So this is not a solution in the wake sector. And in the wake sector, what you expect is the following. So now the particles move apart from each other. So we have this particle here, so sitting in the origin, and you have the second particle that goes along with a very large velocity. So what happens is that it will take some time, of course, for this particle, for example, to rotate in order to fill this probability shadow. And so the extent of this wake will be very large. So the spatial derivatives in the z directions are small, but for small z, the derivatives in the rho direction are extremely large because the G of R is 1 here, it's essentially 0 here, and you have this steep change with rho. that makes the spatial derivative in this direction, in the rho direction, very, very large. And you can use that to determine a solution for the G of R in this wake tractor. Now you can ask for how does the extent of this probability shadow, so the wake, how does this extent scale with the P-Clan number? Now, first of all, the angle over which this particle should rotate to get at rho at the position rho is 0. So then it will fill the probability wake. That is, of course, the extent L, 1 over L multiplied by A, which is the width. So this thing moves here, where the G of I becomes almost equal to 1, and the sine of that angle is A over L, so this distance divided by the extent of the wake, and that is, for a small angle, the angle itself. Now, the time it takes for this particle to rotate over that angle is given by that angle squared divided by the rotational diffusion coefficient, and of course, the extent L of the wake is V0 multiplied by this time. So if you put this delta theta in here and the resulting delta t in here, you get immediately that the extent of the wake divided by the radius of the sphere scales as lambda to the power 1/3. So you can actually find an expression for the pair correlation function in the wake, which is a long calculation, so I'm not going to do that here. It's an integral of a product of Bessel functions, and you see here an exponent where you have an I to the 3rd divided by lambda. So this, here you can also see that the extent of the wake scales with lambda 1 to the power 1/3. And you can show in the derivation of this as a result that the rotational diffusion in this case is dominant. So it's exactly opposite to the front sector, where translational diffusion is dominant. And here in the wake sector, rotational diffusion is dominant. And you can essentially forget about translational Brownian motion.
Yeah.
Now, once you have this G of R, you can derive.
Jan,
yes.
Just to tell you, you have the 5 minutes left.
Okay.
Then after that we will have 10 minutes of questions.
Yes.
So
I will finish in 5 minutes.
Yeah. Anyway, just to warn you. Thank you.
Yeah. Okay. So we know this G of R. You put it in this equation that we had before, and I'm going to ask for the equation of motion of the volume fraction, which is the integral over all orientations of the orientation dependent volume fraction. And what's also important is the swimming direction, which is called the polarization. So you can derive this equation. So if you put in this G of R, you get this equation of motion, which contains, for the volume fraction at a point R at time t, you get a divergence of this polarization. You can calculate actually also from this equation of motion for rho of R and U the polarization, and you get this expression for the polarization. So it's minus the gradient of phi, which means that a gradient in the density induces a preferred swimming direction from high to low concentration. So it counterbalances if you want, for example, spinodal decomposition, where you have uphill diffusion due to strong attractions between the particles. So it counterbalances spinodal decomposition, for example. So if you put this in here, you find fixed equation for large, this is for large lambda. So for large swimming velocity, you find an effective diffusion coefficient that goes with lambda squared, d0, and then 1 minus 2 phi. Of course, you would maybe expect when phi is larger than a half, the effective becomes negative, and you get a kind of spinodal decomposition, but of course, this is only valid for small phi. So to summarize, in the front sector, you have for large swimming velocities, you have a very asymmetric DOR with a high contact value in the front sector where particles approach each other, and a very extended wake where DOR is very small in the wake sector where particles move away from each other. Now, future directions would be to look at intermediate Peak-Length numbers. So we have not been able to solve this equation of motion for the DOR for arbitrary Peak-Length numbers. It will be nice to have a comparison to the numerical solutions and to extend the analysis of DOR to higher concentrations. For example, through a kind of Ornstein-Zernig approach, for which you can write down the fundamental equations, but solving this is another point. And of course, you would like at the end to include hydrodynamic interactions. So this, I hope that I gave you some impression of what swimming does with the pair correlation function. And with that, I would like to thank you for your attention. I hope I'm in time.
Yeah, you were amazingly in time. Thank you very much. We again have time for a short question before entering into a sector of 10 minutes for questions for the two talks by Fernando and by Jan. But let's start with one or two short questions about Jan's talk. Remember that you can pose the question directly by pushing the button to share your video, and please go ahead and do it. And also the people that are already with the privilege of sharing their video, go ahead for your questions. Okay, I do. While people gets ready to pose the questions, let me ask you with respect to Jan, with respect to calculating this which is no longer radial distribution function, but the analog of that. Can you link that property with other properties that you can also measure, just like in the case of equilibrium, your GOR is related with many other properties like thermodynamic properties and so on. Can you comment a little bit on that?
Well, I think, so of course you have this, so do you still see the screen?
Yeah.
So, for example, you can measure, in principle, the effective diffusion coefficient of Fick.
Okay.
But you would also be able to measure, the effect, calculate the effect of swimming on the osmotic pressure, which I didn't do, but I think you can do that.
Okay.
You can obtain an expression for the self-diffusion coefficient with swimming to first order in phi. Okay. And you probably can also calculate viscosity at low concentration. Okay. So I think with this GOR you can do anything. So all the things which you can do with passive systems, but now with swimming.
Okay, good. Thank you. And okay, let me see how can I realize if there are questions coming from the rest of the audience, and that has to do with probably. Can you stop sharing so that I can see? Thank you. Okay, is anybody in the audience posing a question to Jan? Okay. If not,
actually, Magdaleno, if I can ask one quick question.
Please go ahead.
Jan. So Jan, so you described this very nice model for essentially, if I understood well, spherical swimming particles. So how do you expect that this is describing maybe something like a real bacteria? So do you think that it would be very different, or what one should take into account, or what kind of sort of a real system one should study to compare, for example, to your results?
Well, there are, of course, many synthetic colloidal systems in which you could measure, for example, the GOR, or the osmotic pressure, or diffusion coefficients, or whatever. For bacteria that move through by means of these large flagella, these flagella also have an extruded volume, right? So at high concentrations, you would have to include these flagella, which is not easy.
Yeah.
And if the bacteria move by means of Sicilia, then of course you don't have any sort of flagella. And then what you should take into account at high concentration are, of course, hydrodynamic interactions.
If I may, can I ask a question?
Yeah.
Yeah, go ahead.
Jan, how does this approach, formalism and so on, will get more complicated if one should consider, for instance, a small elongation of the particles? Will be that extremely difficult? I mean, in connecting to, I'm very sorry, connecting to the question of Marco. I mean, trying to mimic, let's say, real life active matter and so on will be very difficult to approximate now, this G of R and so on.
Well, what you have to include then is an interaction potential that also depends on the orientation, right? So in the small...
Not to mention the connection between the diffusion coefficient. I'm very sorry.
The risk of
so
internet. Go ahead.
I'm very sorry, but it's very loud here.
So this
sorry, yeah.
So psi that they had, so the total energy of the system, and so the pair interaction potential, they become all dependent on the orientation as well. And that makes life not so easy. But maybe it can be done.
Okay, so there are no fundamental barriers. There is just a mathematical complexity of the problem, or something, if I understood correctly.
Yes, yes.
Okay, there are some questions in the chat, and let me though formally conclude Jan Dhont's talk and questions, and let's now come back with Jan and Fernando for further questions. And Jan, again with you. Martin Oetel is asking, let me check, and how about computer simulations? Can you compare with computer simulations? That's Martin. Would you like to pose the question yourself by pushing the button? You're welcome to do that, but if not, the question is already posed to Jan.
Well, I think I understand the question. So, what people do in simulations, they average the G of R over all orientations. And if you do that, you mix up the wake sector with the front sector. So you cannot distinguish between the two. But what you do find is that there is, in a very small region, there is a steep increase of that G of R. So also if you average over the orientations, you will still see also in simulations this boundary layer behavior. So, and the reason, of course, that they average over orientations is for some numerical accuracy. So it will be very difficult to determine a function that depends on 3 or 4 different variables, right? I don't know if that answers your question. So in simulations, you do see the boundary layer behavior, but what is always also presented are orientational averages of the G of R.
Mm-hmm. Martin, are you Does that
doesn't work.
Huh?
His mic doesn't work.
Oh, his microphone doesn't work. That's why Martin cannot pose the question directly.
It's a no problem.
Okay. Anyway, again, which are the following questions? Felipe Pacheco from Puebla would like to ask, I think that Fernando Donado, about hysteresis effects in his experiments. Fernando, could you address that question?
Yes. I am, well, at the beginning of the experiment, the hysteresis effects are very important because at the beginning particles are not magnetized. So as various cycles of the magnetic field is applied, the particles acquire a permanent dipole moment. But when the particle just acquire a magnetic permanent dipole moment, and then I think or after that hysteresis are not important because particles are not. I mean, particles are rotating, so they are not more. They are not obliged. They are not on the same direction. So as they rotate, there is not the necessity to change its magnetization. I think, but the multiply is so small that I really can't measure that. So.
Okay, Felipe, you are welcome to share your microphone to see if you are happy with the answer. And anyway, you can do it anytime, at any time. Felipe, okay.
Can you hear me?
Yes, we can hear you, and we are very happy to see you, Felipe.
Yeah, hello, everybody. Thanks, Fernando, for the response. Yes, in fact, it was because all the results you are showing are always with increasing magnetic field, I think. So when you reduce the magnetic field, of course, you have some hysteresis normally in the particles, and then I was wondering about this effect. But if you say that it's small, well, I can understand that.
Yes, before I start the experiment of when we decrease the magnetic field, the particles were about 1 hour in the maximum magnetic field we use. So the whatever the particles do with the magnetic field is doing during that period.
Yes,
1 hour approximately before that.
When you decrease this variable, the magnetic field, that is the parameter that you can control in your experiments, when you decrease it or when you increase it, you have some hysteresis always, working on that.
Yes.
Or how
to tell the truth, yes, I believe that there is some effect, but currently I am not able to quantify them.
Okay, thank you very much.
Then I have a question for both of you. I think that you guys are referring to hysteresis effects with respect to one individual particle.
Yes, yes.
Now my question is, would that translate also into some form of macroscopic hysteresis? Let's say, imagine that you change the applied field in the magnitude and go up and then go down. Will you find some form of collective hysteresis, which you would find because the system is a non-equilibrium system without this hysteresis? But would you expect that there is some collective hysteresis coming from magnetic hysteresis?
In fact, I think that Fernando is what is doing more or less when he is using the magnetic field as a parameter to control all these dynamics. He's considering like mean magnetic field in all the sample. No? of course, there should be a small amount of hysteresis in each particle, and well, this hysteresis is not going to be the same in each particle, because at the center of the system, I think that it would be a larger hysteresis than in other parts, right, Fernando? So I think that you could estimate a mean hysteresis, but well, I don't know if you can do that, Fernando.
I am not sure if I can do it, estimate this effect. When Magdaleno was asking about the hysteresis, I was thinking about the system as a whole. When, for example, in the experiments, when crystallines are obtained, this is a kind of hysteresis, because the system, it doesn't work in the same way when the magnetic field is decreasing, and then if we increase again the magnetic field, the system is not the same, because the particles are together, and then the magnetic field they feel, okay, particle field they neighbor, and then the effective magnetic field or the magnetic moment is a little different. So I was thinking in that in that phenomenology.
Okay. Okay. More questions from the audience. Remember that you just ask for sharing the microphone and pose the question. I don't see questions in the chat either. So
I do have another question, Magdaleno.
Oh, go ahead, please.
Fernando, in your experimental system for magnetic particles, would it be possible to consider mixtures of non-magnetized particles that might affect what you observe, and also of particles which might have a different magnetization, and then trying to study whether the physical scenario changes upon this kind of changes?
It is possible to work with that. In a work we published years ago, we experiment with non-magnetic particles, and a magnetic particle was used as a thermal bath for that particles. Currently, we were wondering if using polystyrene particles in the middle of the magnetic particle could be interesting. So, currently we didn't do more in that direction. However, if you or anyone is interested to collaborate with us, with pleasure, we experiment with any forms of the particles. Currently, we have two particle size, some polystyrene particles. What else? That's all. But we can change the experimental setup as we can.
And in connection with this question, if I understood correctly, you have to put your experimental particles for quite long in the strongest field that you can reach, right? Otherwise, you will have different magnetization, possibly, or something like that.
Yeah.
Would it be possible to magnetize differently the particles in order to check whether you can have some sort of polydispersity in your system? And then, I mean, this might be like two ways of studying disorder in your system, no? If like removing the constraint of having almost identical particles, and then having particles without magnetization, or particles with a, I don't know, a distribution of magnetizations which might respond different to your external field, and then realizing this kind of effective Brownian motion differently mediated by the response to the field. Would be that possible?
Yes, fair. In fact, it's a wonderful idea. I will take that idea and I will try in
We
the
might discuss in Pachuca soon enough this idea, if you will.
Yes, yes, it's a wonderful idea.
Yeah.
I never tried that. You're right. We can take a batch of particle, put in a magnetic field. We take another batch of particle and under a different magnetic field, and then we can mix them. Yes, there will be a polydispersity of magnetic.
I will be very pleased to participate in
Yes,
such a project.
Yeah. One of the purposes of these sessions is exactly that, to agree or to start to envision some form of collaboration. So thank you very much. Let me see. I wonder, because I also have a question for Jan, and with respect to spinodal decomposition, if you allow me to. Jan, one of the effects of activity, my understanding is to produce some form of effective, under some conditions, of effective attractions, and that leads to spinodal decomposition occasionally. But you were also saying, let's say, you were concluding sort of the opposite, that this effect that you calculated signal in the opposite direction. Did I understand correctly, or I misunderstood something?
Yes, I think you understood correctly. So there is, if you have a concentration gradient, then there is a preferred direction of orientation that points from high to low concentration. So the particles swim in a direction that is downwards, so from high concentration to low.
Okay.
And of course, spinodal decomposition is exactly the opposite, right? So due to strong interactions between the particles, there is an uphill diffusion, which leads to demixing.
But then my question is, but anyway, there is this overall effect of attraction, even if the particles are hard spheres, but they are active. Mm-hmm. My understanding is that even under those conditions, there may be an effective attraction leading to spinodal decomposition. But then the effect that you described that goes in the opposite direction, is it one correction to that, or how it relates to that primary effective attraction?
Well, I'm not so sure if you can interpret this. So you could interpret the wake as a kind of long-range attraction, right? But on the other...
Okay. Because you have the wake and the front, and they go in.
Yeah, but in the front sector, you have a very strong short-range repulsion. So if you want to interpret this G of R as the exponent of some potential, then that potential would be long-range attractive in the wake and very steep, strongly repulsive in the front sector. Okay. And apparently the front sector wins.
Okay.
So if you integrate over all orientations, then apparently the front sector is more important in the repulsion of those particles than the wake sector. Mm-hmm. I'm not sure if this answers your question.
Yeah, I think so. So. Yeah, thank you. Okay, Benny, do we have questions in the chat? Okay, apparently we don't have any other questions at the moment. So that would conclude the first set of two talks with the questions, common questions. But before leaving, is there anybody else wanting to add anything to this first portion of our